Hello everyone, I'm Hongzi. I'm going to talk about our work learning scheduling algorithms for data processing clusters. This is a joint work with Maud, Shailesh, Mohammed from MIT, and Zili from Tsinghua. Scheduling is a fundamental task in many computer systems. It serves as a core component in cluster managers like Kubernetes and Mesos, or data analytics frameworks such as Spark or Hadoop MapReduce. Improving the efficiency of a cluster scheduler is the key to save operation cost. And today's large enterprises like Google, Amazon, and Facebook deploy the cluster infrastructure in the scale of billions or tens of billions of dollars. At this scale, even a fraction of improvement in the scheduling efficiency can save millions of dollars. However, designing efficient cluster schedulers often needs to consider many different factors. This requires very good understanding of the system and the workload. For example, scheduling jobs with dependency structure is inherently hard. Besides the algorithmic challenges, there are also model complexity. It's very hard to accurately model the intricacy of a complex system. As an example, in data center with different network quality, it's hard to trade off between massive distributed computation and data communication over the network. The right balance really depends on the particular system. Also, practical scheduling often becomes a messy problem with all sorts of constraints. There can be hard constraints like hardware placement constraints, or soft constraints such as data locality constraints. Now, because of all the complexity and potential efficiency improvement on the table, there's been a huge body of prior work and human engineering gone into this domain. Each of this work targets a specific aspect of the scheduling problem. However, in practice, if you look at the state of our cluster deployment, they either sidestep the complexities and resort to simple heuristics such as fair sharing or even FIFO scheduler. Or, in other cases, the more sophisticated system involves very complex configurations, which require expert tuning with dozens of parameters at the same time. As a result, there isn't really a fixed, one-size-fits-all scheduling algorithm that performs optimally in all scenarios. The optimal solution really depends on the specific system and specific workload it's deployed on. Therefore, centered around our research, we ask, can we use machine learning to help taming the complexity of building an optimal cluster scheduler? In other words, can we use machine learning to automate the process of finding highly performant schedulers in different workloads and different systems? In our work, we built Decima, which learns workload-specific scheduling algorithms automatically through experience. We focus on scheduling jobs that are structured as directly acyclic graphs, or DAGs, which is a common abstraction to many modern computing clusters. In this setting, each node of the graph represents a computation stage. Each stage contains identical tasks that can run in parallel. So if a stage is assigned with more cores, the tasks can run concurrently and finish faster. The edge in the graph represents data dependency. This means the child stage cannot start to run until all its parent stages have been completed. In a typical data center, users continuously submit many different jobs online over time. And the task for a scheduler is to map the pending computation stages onto available servers to run. In our design, Decima uses reinforcement learning to automatically learn the cluster scheduling algorithm by interacting with the cluster environment. For concreteness, we developed Decima in the context of Spark. At a high level, a Decima scheduling agent observes the information of all available jobs and the status of servers at every scheduling event. The agent then takes a scheduling action, which uses a special neural network to map a certain amount of servers onto each job. As a feedback, the cluster environment sends the agent a reward signal corresponding to the runtime of the jobs. Trained with reinforcement learning, Decima explores different scheduling policies and improves its performance with large amount of interacting experience with the cluster environment. Now, before we go into the technical details of Decima, let's first see a demo. Let's see how different schedules make a difference in terms of job runtime. Here, different jobs are marked with different colors. The size of each node corresponds to the log scale of total work in that computation stage. On top of each job, we use orange squares to visualize the number of servers working on the job. On the left-hand side, we will animate the schedule of all the jobs on a canvas. The x-axis is the time, and the y-axis shows the status of 20 servers. The color on the canvas will show which server is working on which job from the right. The purple color means the server is idle. So let's first see what a FIFO schedule looks like. Each red line indicates a job completion event. As expected, this simple scheduler reserves the servers to the jobs at the order of their arrivals. Since it does not consider the size of the job or resource sharing, when a big job blocks ahead of many small jobs, this significantly increases the average job completion time. In this example, the average job completion time is 225 seconds. Now let's have a look of shorter job first, which reorders the execution based on the total work of the job, and it assigns all the servers to a job at a time. Even though this is a very simple heuristic, just by finishing small jobs quickly early on, this already improves the average job completion time by almost a half compared to the FIFO scheme. At the end, the average job completion time is 135 seconds. Another widely used heuristic is fair sharing. It equally spreads out the servers to all the jobs, and when a job is done, the other active jobs will equally share the servers that just become free. In this case, each server has a higher chance to have available tasks to run, and this keeps the server busy at all times and improves resource utilization. Now let's compare shorter job first and fair sharing for a second. We would expect shorter job first to perform pretty good on average job completion time, but it turns out fair sharing is doing a lot better even though it does not prioritize any small jobs. This is because in practice, shorter job first can generate more work. And it turns out that the idle server time in the shorter job first don't cover for all the extended areas. The ballpark actually comes because each parallel server has to individually read shards of data. For some jobs, the I/O dominates over the benefit of parallel compute. In other words, each job has an inherent efficient degree of parallelism. Assigning more servers beyond the efficient point generates unnecessary work. Decima learns to leverage the advantages from shorter job first and fair sharing. It learns to selectively focus the servers on certain small jobs to finish them quickly while still leaving no resource idle. Comparing Decima to fair sharing, Decima is able to prioritize jobs much better, where it packs many small jobs to finish them early on. And at the same time, it still uses resources as efficient as the fair scheme. So even on this simple demo, an optimal scheduler has to weigh different factors, like the ordering of the jobs, the resource sharing, and the inherent degree of parallelism. Optimizing the scheduler based on different systems and different workload is very tedious and difficult. Decima automates the process of finding an efficient cluster scheduler. Our main contribution with Decima is that it's the first time to show it's even possible to apply reinforcement learning to cluster schedulers that handle complex data processing jobs. To successfully learn efficient scheduling algorithms in practice, we encountered several challenges. Decima goes beyond just applying off-the-shelf reinforcement learning algorithms. We developed new learning methods that enables reinforcement learning training for online stochastic job arrivals. Moreover, the cluster needs to handle job decks with arbitrary shape and size. We therefore developed a special graph neural network that can process this kind of input and use it to express scheduling actions. The first challenge I want to highlight is that in practice, jobs arrive in an online streaming fashion. To handle this continuous job arrival, the reinforcement learning agent has to experience the arrival pattern during training. Why is this difficult? Well, we find the training is very inefficient if we just simply feed the agent with many long sequences of jobs right from the beginning. The reason is that reinforcement learning training starts from scratch. The initial random policy performs very poorly. The agent cannot schedule to finish the jobs as quickly as they arrive. If we monitor the number of backlog jobs in the systems over time, we will see the agent is simply overwhelmed by too many jobs arriving, and the jobs just keep queuing up without being processed. This happens for all initial training iterations. Now, letting the agent explore beyond a few steps in these early iterations wastes training time, because this overloaded cluster scenario will not occur with the reasonable scheduling policy. Clusters normally don't operate in this region. The learned policy will not generalize if we keep training it with the experience data coming from this region. So what we do is we early terminate auto exploration for early iterations. This way, the agent can reset and try again from an idle cluster state. As the training progresses, the agent improves its scheduling policy and can keep the cluster stable for longer time. At this point, we gradually increase the job sequence length to let the system run longer before resetting. This keeps the scheduling problem more challenging and steers the agent to learn stronger scheduling policies over time. This concept of increasing the learning difficulty level during training is a form of curriculum learning. The second challenge we discovered is more subtle. A strong scheduler needs to be robust to the variations in the job sequences. It's also well known that in practice, the job size distribution is heavy-tailed, which creates huge amount of variance. In order for the agent to learn robust scheduling policies against workload variations, we need the training set to contain a wide variety of job arrival patterns. Now, this variance in the job sequences becomes a problem that can throw off the reinforcement learning training process. Let me use an example to show this problem. Let's say we have a few jobs arrived. At time t, we'll make a scheduling action AT. Recall that reinforcement learning trains the scheduling agent by assessing how good the action is from the empirical data. It compares the empirical total reward following action AT with an average case baseline for state ST. And reinforcement learning will increase the probability of the actions that lead to better than average rewards. Now, after this scheduling action, just by chance, there can be a burst of large jobs coming in the near future. Under this workload, the cluster is inherently overloaded, and every scheduling policy will take a long time to drain all the jobs. As a result, the reward you receive will be very low with these large jobs. By contrast, a stream of small jobs is easier to handle. Any sensible scheduling policy will finish these jobs quickly, and you will receive large rewards. However, notice that the difference in the reward has nothing to do with the action at step T. It's purely due to the randomness in the job arrival pattern. This randomness confuses the training agent because it relies on the reward to assess the action. To remove this variance, we need to explicitly take the job arrival pattern into account when estimating the score for the actions. Intuitively, we want the average case baseline to depend not only on current state, but the job arrival pattern as well. This is the idea behind an input-dependent baseline. What this new baseline means is that we want to estimate the average case reward conditioned on the particular job arrival sequence that we encountered during training. This method removes the variance from the job arrival sequences. In our experiment, we also empirically find that it improves the performance of our scheduling policy, especially when it handles long sequences of job arrival. In fact, this technique of removing variance is applicable to many other systems that have an external input process. For example, it also applies to adaptive video streaming when the network bandwidth is an external input. Even robotic applications with external disturbance can benefit from this approach. We published an ICLR paper for more mathematical details. The third challenge I want to highlight is how we process the job information and use it to express the scheduling action. Standard reinforcement learning applications use neural network to process vectorized inputs such as images. But our scheduling problem requires the reinforcement learning agent to take graph-structured input. Each node in the graph embeds the information in a raw feature vector, which includes information like number of tasks, the task duration, number of servers already assigned to the node, and so on. Also, the number of jobs in the system is not predetermined with online job arrival. Therefore, we need a scalable way to process the information embedded in any number of job tags. To do this, we adopt the idea of graph neural network. In the interest of time, I cannot go into the details, but the high-level concept is that graph neural network can express multiple functions over the graph, like assigning a score for each node. What makes graph neural network scalable is that the function is broken into small local operations everywhere in the graph. In our paper, we also describe how we customize graph neural network for our scheduling application. Now that we can use graph neural network to compute the value onto each node, we still need to express the scheduling decision. So let's step back. Scheduling is essentially expressing a mapping between runnable stages and available servers. Now the question is, how do we encode this mapping so that the reinforcement learning training is easier? As a simple attempt, one option is to just directly ask the agent to output the mapping. This immediately results in an exponentially large action space because the action space has to contain every single possible mapping. This quickly becomes invisible to express when the number of servers or number of jobs becomes large. Another option is to output the mapping through a sequence of actions. Each action decides the assignment of one node onto one server. Each action only needs to pick the node, so this reduces the action space to the number of nodes in the system. But this will lead to very long action sequence because at each scheduling event, there can be as many actions as the number of free servers. Long action sequence is known to be a hard problem for reinforcement learning since it's hard to assign credit to an action for the reward signal. Decima uses a two-dimensional action design to balance between the size of action space and the length of action sequence. For each action, it outputs a node selection and the number of servers assigned to this node together. So from a pool of identical servers, at each step, we'll pick a node and specify the number of servers assigned to this node. In the next round, we'll pick a different node and assign it with some servers from the remaining pool. This process continues until all available servers have designated nodes to run. By expressing the parallelism limit as a single number on each action, this design increases the action space a little bit, but reduces the sequence length by a lot. In our evaluation, we also find this is the only design that allows us to efficiently train Decima. Now I will show you a wide range of experiments that we did. We first compared Decima with existing scheduling heuristics. Here's an experiment with batch job arrival. The workload is TBCH jobs with different sizes. We trained Decima on a Spark simulator. After training, we evaluate Decima with unseen job combinations on a real Spark cluster. The testbed has 50 CPU cores. For this problem, we actually sit and try very hard to hand-tune a strong heuristic. The blue line is a tuned weighted fair scheme based on job size and resource sharing. From this CDF, Decima improves the average job completion time by 21% to 3 times over the baseline schemes. A more realistic evaluation is with online job arrivals. Here we run 1,000 jobs with a Poisson arrival over a period of 12 hours. The figure on the top shows the time series of number of concurrent jobs in the system. We only show Decima and the best comparing heuristic. The bottom figure shows Decima's job runtime relative to the heuristic at each 1 hour period. The bar plots below 1 means Decima finishes the job faster. On average, Decima achieves 28% lower average job completion time than the best heuristic. More importantly, in the busy period where the cluster is heavily loaded, in which case the scheduling problem becomes more challenging, Decima achieves almost 2x better runtime than the baseline. Now, to better understand what Decima is doing to outperform other schemes, we plot the job runtime for those 1,000 streaming jobs in the y-axis, and we put the corresponding total work on the x-axis. Each dot represents a job. Empirically, Decima finishes small jobs particularly faster. On the right, we look at the number of servers assigned to different jobs. We can see that Decima prioritizes small jobs by assigning them with more servers. Notice that Decima learns to give small jobs the right amount of servers, but not too many servers, because otherwise the cluster will have been overloaded with unnecessary I/O work, similar to shortage of first you saw in the demo. Decima can also apply the same learning method to other scheduling problems, like multi-resource packing. Here we use a month-long production trace from Alibaba. We train Decima using the first half of the trace and evaluate the scheduling policy on the second half. Using the same training method, but only adding the memory requirement in the features, Decima can learn strong scheduling policy that outperforms state-of-the-art schemes like Graphene or Tetris. Due to time limit, I can't cover all the details in our evaluation, but our paper described the impact of each component in our learning algorithm. We evaluate the generalization of the learn policy in different workload or larger clusters. We also measure the training and inference speed, how Decima handles missing information such as task runtime, and comparison to the offline optimal. As a summary, Decima uses reinforcement learning to generate workload-specific scheduling algorithms. Decima goes beyond just applying existing reinforcement learning methods. We develop new learning algorithms so that Decima can handle online stochastic job arrivals. Decima leverages a specially designed graph neural network to process job information and use it to express efficient scheduling actions. In our experiments, Decima is able to outperform existing scheduling heuristics, and the techniques we built are applicable to many other systems. More information and open source code can be found in our website. With that, I'm happy to take any questions. Thank you.